I really love it.
Yes. Yeah. Oh,
So, okay, I believe the recording is in progress now.
okay. So we're good to go.
Yeah, so I'm going to introduce you just very shortly. So, hello
Yeah.
everyone. Thank you very much for attending the first part of this series of seminars on the James Webb Space Telescope. This is part of the Canadian Telescope Seminar series that we are doing at the GSC since a lot of years now. Um, Today we have the pleasure of having Dr. Heidi White with us. Heidi White is an outreach officer at the Trotti Institute for Research on Exoplanets and at the Observatoire du Mont Mégantic in Quebec. She obtained her PhD in astrophysics in 2021 at the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto. She specializes in star formation and galaxy kinematics. Her area of expertise is the evolution of galaxies at cosmic noon, which refers to the period in the history of the universe that was 10 billion years ago, when star formation in galaxies was reaching an all-time high. So now I will leave the stage to Heidi, and she will tell us about Canada's role in JWST's groundbreaking science. Thank you, Heidi.
Thank you, Adrien. So hello, everyone. As mentioned, my name is Heidi, and I am speaking to you today in my capacity as outreach scientist for the James Webb Space Telescope on behalf of the Canadian Space Agency. But as mentioned, I also hold a role as outreach scientist at Université de Montréal and IREX and for Observatoire du Mont Mégantic. And today I'm going to be presenting what is the first half of a duo lecture series on the James Webb Space Telescope for CaTS. And today, what I'm going to do is sort of give you an overview of JWST for those of you who are new to the telescope. I know that you're all grad students, and so I am assuming nothing about your prior knowledge here. I know that when I was a graduate student, it was not all that long ago, there were so many observatories, so many telescopes, and even as an observer myself, it was hard to be up on absolutely all of them, right? And I would go to Casca and I would hear people talking about different observatories, and I'd have to. So I am not going to assume that you are pros at JWST. I'm just going to provide a general overview today and sort of take you on a journey through the science of JWST from its incredible engineering to now its groundbreaking discoveries that are happening here in Canada. And what I'm going to do is try and focus on the role that Canadian astronomers and instruments have been playing in unlocking some of the mysteries of our universe. So I kind of want to take a second, because you're all graduate students, about sort of my path to being in this role. So as mentioned, I got my PhD at U of T. I focused on galaxy evolution, but I also, throughout my PhD, did a lot of outreach and education. And the reason I mention this is because one thing that I think we don't always talk about as much within the academic community is about alternative career paths aside from just going on and doing a postdoc. And my career path is an example of that. After graduating with my PhD, I did not do a postdoc. I went on to work in outreach and education. And I know that when I attend Casca, I always have grads coming up to me and asking me, how does that work? I'm interested in doing education and outreach, but I don't really know what that looks like after I graduate with my PhD or my master's. And so I just wanted to put up this slide here, sort of describing what my job is now. For the CSA, in my role, I mainly provide the Canadian public and the academic community with general information about JWST, a lot of the work I do is actually in public relations and media representation of the discoveries that are happening within Canada. So I support a lot of the researchers who are doing science with JWST in communicating their results to the general public and amplifying their results. And then I also do a lot of work in terms of managing funding grant for JWST and representing the discoveries in the media. So actually doing interviews on behalf of Canadian scientists and doing a lot of science communication. And so if you have any questions, it may be the case that some of you are also interested in pursuing a career in education outreach. And so if you have any questions, I put my contact information there. I'm happy to speak in both English and French. And you can feel free to just email me. And yeah, anyway, I just thought I'd offer, because this was not something that was offered to me very much when I was a graduate student. And I felt quite out of my depth in terms of being able to turn what was an education interest and outreach interest into a career path. So JWST, right, James Webb Space Telescope, this is a revolutionary telescope that is completely transforming how we see the cosmos, really. It is allowing us to look deeper into space and further back than we've ever been able to before. It is capturing light from some of the first galaxies that formed after the Big Bang. It's allowing us to do much more detailed studies into, sorry, that's my dog barking, exoplanets. It's allowing us to peer into stellar nurseries and study the chemical composition of planetary systems. And in a sense, this is why I'm here to talk to you about this telescope today, because Canada has played an absolutely crucial role in the development of the telescope and is now playing a big role in the science that's being done with it. And this is why discussions about JWST really matter, right? And in my presentation today, what I'd like to do is sort of provide a whole lot of context for the telescope and how it was developed and the science that's being done. And then my colleague, Loic Garbert, will join you next month sometime, and we'll be discussing more of the nitty-gritty of how the instruments specifically work, how exactly they were developed. He works in instrumentation, and the details of like pipelines and data analysis. But for today, we're going to be talking about why JWST matters and what kind of an impact it's making. And so the talk is going to cover three main areas. I'm going to start off talking about the design and engineering of JWST, the science. We're going to be talking then about like some fundamental questions about the universe that it aims to address, and then talk about the science that the telescope is enabling, in particular, the contributions from Canadian researchers. And this is just a little bit of a flow chart, little diagram for the presentation. And at the end, I'm going to be focusing on highlighting some of the most exciting Canadian-led discoveries so far. And the reason for that is because it's going to be a lot more recent stuff. And the reason for that is because ultimately, it's what allows us as researchers to connect with the public. The discoveries that we make that then go on to be viral in the media, it allows the Canadian public to sort of understand the investment that we've made as a scientific community and why the science is so important. So that's sort of my bias as a science communicator. It's always important to remind ourselves of that, the power that that has. So Canada has played a vital role, as I said, in JWST's success. And this is mainly by providing two key components for the telescope. So this includes the fine guidance sensor. This is what keeps the telescope locked on its targets, and the near-infrared imager and slitless spectrograph. That is a mouthful. This is what's known as NIRISS, which is allowing us to do really crucial exoplanet and deep space studies. And the reason I mentioned this, this is, I believe, this is the fine guidance sensor NIRISS at NASA Goddard before it was integrated into the instrument module. But the reason I say this is because this illustrates that Canada is not only just a partner in the mission, but was an essential contributor to JWST. And I think it's important to highlight because often when I hear JWST referenced, when I'm speaking with the public, for example, the telescope is really associated with NASA, right? Sometimes with ESA, but it's usually NASA. But the CSA and Canadian researchers have played a really big role in this. And so it's important that within Canada, we remind ourselves of that a lot of the science that's being done is because of the hard work of Canadian researchers. The development of these two Canadian-made instruments, apologies, was led by Professor René Doyon and Chris Willett, Dr. Chris Willett from NRC Hertzberg, and the Webb Science team here in Canada. And so here we have an sort of image describing the fine guidance sensor. So this is an infrared camera that functions like JWST's eyes. So when a telescope wants to take clear images, it needs to point towards the object it's studying and really track it very carefully in the sky. And so the fine guidance sensor allows us to get clear and detailed pictures of the universe. It locks onto a star with very high precision. And in some ways, you could argue that this is the most important thing that Canada delivered for the telescope because all scientific observations taken by Webb involve in some way the use of the fine guidance sensor. And then there's NIRISS, as I said, the near infrared imager and slitless spectrograph. So this instrument photographs and deconstructs light collected from objects in space to show us exactly how bright an object is at different wavelengths or colors, spectrograph. And this allows us to get detailed information on the characteristics of the observed object. It is sensitive to infrared light between 0.6 and 5 microns. And then the light can be broken up into a spectrum using a tool called a GRISM, which if you happen to not be familiar with the GRISM, it's sort of similar in ways to how prisms can break up sunlight into a rainbow. And there's two main ways in which it's being used, but obviously NIRISS can be used in other ways. But one of the big ones is by looking at redshifted light from early galaxies. This is light whose wavelengths, in which the wavelengths have been stretched out due to the expansion of the universe. So NIRISS will allow astronomers, or does allow astronomers, to determine the distances, ages, and chemical compositions. And this is really important for identifying some of the first galaxies that formed after the Big Bang, as I said, and for understanding how galaxies evolve over cosmic time. It's particularly interesting use of NIRISS for me as a galaxy astronomer. NIRISS also is allowing us to be able to study the atmospheres of exoplanets and be able to determine their composition. I'll talk a little bit about this, more specific examples from Canadian research later, but if you're familiar at all with exoplanets, I'm not an exoplanet astronomer, but I have been working at an exoplanet institute for the past couple of years, and so I've learned a lot about exoplanets. You'll know that the state of the field is really getting to a place where we know that exoplanets exist, right? Thousands of exoplanets have been confirmed. And we're shifting exoplanet science more into characterizing the planets and getting more information about them themselves and sort of building holistic pictures of the planets. And so this is where NIRISS is really, really playing a powerful role because it allows us to study exoplanet atmospheres through transmission spectroscopy. So basically, it observes how a planet's atmosphere filters starlight as the planet transits in front of its host star. And so it can break down this filtered light into its component wavelengths and detect things like, molecular signatures like water vapor, carbon dioxide, methane, etc., to provide us insight into the atmospheric composition and possible clues about whether or not a planet can be habitable or not. And so this instrument is also helping astronomers characterize a variety of exoplanet environments, from hot gas giants to, potentially habitable rocky worlds. Now, within just the first few months of becoming operational, JWST exceeded its expectations. It was delivering breathtaking images and groundbreaking scientific data. And this image, which was one of the first releases, a deep field image that contains thousands of galaxies, and some from, I think, upwards of 13 billion years ago. And the level of detail and our ability to see different morphologies and structures that were once invisible to us really highlights why it is the most powerful telescope ever built, that humanity has sent into space. And so now I'll talk a little bit about how that telescope exactly came together. So whenever we're designing a telescope, right, the first thing we need to think about is what kind of light we want to capture. That is, we build telescopes to observe different parts of the electromagnetic spectrum. And depending on the science we want to do, that also dictates the part of the electromagnetic spectrum we want to observe, et cetera, et cetera. They're all coupled together. So this is a really important design element. And JWST operates, as I said, in the infrared portion of the electromagnetic spectrum, between 0.6 microns and about 28.5 microns. This is sort of the visible reddish light to the mid-infrared, or actually, no, that's near-infrared to mid-infrared. And that allows us to observe objects that were either too distant or too cold to be able to be seen in visible light. And this, I put up here this image because it's, we talk a lot about Hubble and JWST being the successor to Hubble. And truth is, yes, in some ways, they're both space telescopes, and they both have had a huge impact on how the general public sees the universe and connects with the universe. But they also observed slightly different parts of the electromagnetic spectrum. So there are important differences there. And so in this way, JWST is really unlocking a new type of, science for us. And so you could ask, why would we want to focus on infrared light? Well, the universe is expanding, and as it does, light from, for example, distant galaxies are stretched to longer and longer wavelengths. This is a process we know of called redshift. And by observing in the infrared, JWST can detect this ancient, I guess you could say, light, allowing us to study galaxies as they were billions of years ago and penetrate dust clouds to see, for example, newborn stars and planets. And so this is two major examples of why infrared light is an important wavelength regime that we want to target, and in particular with JWST. Now, another important design element, this is a schematic that I have used in a number of talks, from all the way from town halls to public outreach events for middle school kids about JWST. But there's a reason why we put JWST in space, and this is because observing in the infrared from Earth is really, really hard, right? So here you can see a schematic of sort of the transmission of the Earth's, the opacity, I guess you could say, of the Earth's atmosphere. So for example, it says here, most of the infrared spectrum is absorbed by atmospheric gases. So you have to go out to space if you're going to do a good job doing it. It's very hard. Well, it's more challenging, we'll say. It's not impossible, but it's quite challenging to observe in the infrared from Earth. I can tell you that from firsthand experience as a PhD student who did multi-wavelength work. Infrared, near infrared is quite challenging even then, because of the Earth's atmosphere. The atmospheric effects really hinder if it were on the ground, a telescope's ability to observe these faint distant objects. And so because it's in space beyond the Earth's atmosphere, JWST can operate freely in the infrared range and provide really clear, crisp, uninterrupted data essentially for its mission to observe the deep universe. And so that's another important design element to keep in mind for JWST. This is why it's a space telescope. Now, in terms of its engineering, the telescope, the observatory effectively in space, it has a number of key features, right? So I've highlighted a handful here today. Includes things like, its primary mirror, its sun shield. We have the cold side, which is effectively the side that is where the observations are happening, and then the hot side, which is where this is facing the sun, etc. And this is where we're not necessarily doing observations because it's the infrared. We need to be very careful about this. So the design of the telescope itself is also highly, intrinsically influenced by the fact that it is an infrared telescope. It has, as I said, this massive 6.5 segmented mirror. It has a 5-layer sun shield that you can see here. It's sort of those pancake layers together. It is indeed 5 layers in this image. I don't know if you can see my cursor, but right here, this also additionally folds out a bit. And that sun shield allows it to stay cool and keep these state-of-the-art infrared instruments at proper operating temperatures. And all of the elements that you see here are what allow JWST to be able to capture these incredibly detailed and beautiful images and spectra of distant, planets, stars, and galaxies. So we have to start off by talking about the mirror, right? JWST's mirror is the largest one ever sent to space. It's made of these hexagonal segments that are coated in gold to help. I believe the gold enhances the reflection of the infrared light. And certainly it was massive. It was so big that it had to be folded up to fit inside a rocket and be launched into space. And the importance of this large mirror is that it allows JWST much greater sensitivity, allowing it to detect much fainter objects, in particular in the early universe. And you can see here, I've put an image at the lower left of the JWST primary mirror compared to Hubble's primary mirror, and then a human being. JWST is about 100 times more sensitive than the HST, and it's due to this larger mirror and its ability to capture fainter light from distant objects. And there's a well-known analogy for JWST's sensitivity that it is so sensitive that it would be able to detect the heat signature of a bumblebee flying on the moon. And I love that analogy. I think it really gives you an idea for just how sensitive this telescope is. And then there's the sun shield and cooling system that we saw. The sun shield is about the size of a tennis court, and it's essential for keeping those instruments, these infrared instruments, cool, because infrared light is essentially heat, right? It has 5 layers, and it is able to reflect sunlight and dissipate heat to lower temperatures on the cold side to nearly, I think, minus 230 degrees Celsius. And this is incredibly important, these thin shields. You can see the engineers rolling out here, because without this cooling system, without this sun shield, JWST's heat would interfere with its ability to detect these faint signals, right? So we need to keep the infrared instruments very, very cold, and a huge part of that is this 5-layer sun shield. Now on board, there's 4, I'd say, main instruments: NIRSPEC, MIRI, NIRCam, and NIRISS. And I'm going to take a little time to talk through each of these because they serve different roles. And I think it's useful as graduate students, you kind of understand the purpose of each of these so that when you attend CASTA or meetings or, I don't know, colloquia, etc., different conferences, oftentimes you're just going to get the acronym, right? And so providing some context for what exactly are we referring to when we say these acronyms, I think is pretty important. Each of these instruments has a very specialized role. So here we have NIRSPEC. This is the near infrared spectrograph. This was a primary contribution by ESA, and it's a very powerful spectrograph. It's capable of observing, I think, up to 100 objects at once in the near infrared. And it allows the telescope to be able to do larger scale surveys of, for example, distant galaxies, etc. MIRI is the mid-infrared instrument. It operates in the mid-infrared range, allowing it to study cooler and more distant objects that emit at longer wavelengths, like forming stars, distant galaxies, and the birthplaces of planetary systems. It has a camera and spectrograph, so it can capture these detailed images and spectra, and this was joint between ESA and NASA. There's NIRCam, primary contribution by NASA, so that's the primary imaging instrument, allowing us to observe the universe in the near infrared and take these really, really beautiful images often that we see that become popular in the news. And then there's NIRISS, as I mentioned. This is the Canadian contribution. It's designed to observe these faint objects in the near infrared and, in particular, do spectroscopy of exoplanet atmospheres, early universe, star forming regions, etc. We get high resolution spectra and images from NIRISS. And an example of that I just wanted to highlight, when I say observing exoplanet atmospheres, as I said, this allows us to be able to look for chemical fingerprints of molecules like water, methane, carbon dioxide, etc. So this is WASP-96b. This was the first, JWST's first exoplanet atmospheric spectrum, revealed in July 2022. So this was part of the instrument commissioning first results. And this was work that was part of a Canadian collaboration. So you can see here the spectra. On the vertical axis, you have the amount of light blocked, and on the horizontal axis, you have the wavelength of light. And you can see here those signatures that are marked off from water that are, being detected from within the exoplanet's atmosphere. Now, as I said, the mirror is really, really big. So you put all of these pieces together into a telescope, an observatory, but you got to get it out into space, right? And so ESA played a huge role, the main role, in getting the telescope out into space, launching it, and in particular through the Ariane 5 rocket. So JWST was launched on December 25th of 2021, and it lifted off aboard the Ariane 5 rocket from the Space Center in French Guiana. And because the mirror was so big, you had to fold it up inside this rocket and then deploy it through a series of carefully choreographed steps. And there's this really fantastic documentary on the deployment of JWST that I saw at a conference this summer. And I think it was done by NASA. And they showed the faces of the ESA researchers who were watching carefully as this thing unfolded and launched. And it was, you could see the stress on their faces. There were so many fail points for this telescope that it really is an engineering marvel that this whole thing unfolded so beautifully. And part of the reason for that is that, every single step in the deployment, from the sun shield unfolding to the mirror alignment, etc. Everything has to work perfectly because there's no way to repair it once it goes out into space. So there's a huge investment financially and in terms of just people power, energy, time, getting this thing into space. That's this careful dance that JWST had to do to actually unfold perfectly, had a lot of us on the edge of our seats. Yeah. And so here you can see a bit of a schematic showing the different stages. So you have the deployment, and then the sun shield goes out, and then you have all of the layers that start to deploy, the unfolding of the secondary mirror support structure, and then the deployment of the two primary lateral wings, and then finally the telescope fully unfolded. And this is not as fun as sort of seeing it live. So hopefully this works. I have a video embedded from NASA showing let's see if I can get it to play. So this is the nominal deployment sequence. I don't know if you have the audio, perhaps not, but that's okay. It's just kind of music. And shows you the different stages at which everything is going. So you see it all folded up. So it launches, and then about 4 days later, this is where we find ourselves. After 5 days, momentum flap starts to deploy. You can watch the sun shield begin to unfold. So that sort of video gives you an idea of sort of the as I said, this choreographed dance that needed to happen in space in order for the telescope to operate. I find it very inspiring because, as I said, there are so many points where that system could have failed, and it worked absolutely perfectly, which is really a testament to not only the hard work of researchers, but I think it's a fantastic example of what happens when many nations and humanity comes together to work together to put our minds together to do something absolutely phenomenal and groundbreaking. It is like a fantastic example of teamwork. And certainly given the whole political environment, I think it's a healthy reminder that humanity can come together and do incredible, remarkable things. So where is JWST now? It is now at L2. It orbits the sun at the second Lagrange point, L2. It's about 1.5 million kilometers from Earth. And for those of you who might be less familiar about what a Lagrange point is, this is a location in space where basically the gravitational forces of large bodies, in this case, the Earth and the sun, balance out the centrifugal force felt by an object. And it creates a stable position where smaller things like satellites or telescopes can remain in a relatively fixed position with respect to the other two bodies. There's 5 Lagrange points, I believe, with L2, which is where JWST is, being the one that is pretty popular because it allows telescopes to remain in really constant alignment with Earth and the sun. And it's a location that's really perfect for infrared observations because it allows JWST to keep the Earth, the sun, and the moon behind its sun shield at all times. And so by staying in this stable location, JWST can avoid the heat contamination and make its really sensitive instruments. As you can see here, a little schematic from ESA about Webb's journey to L2. You can see within the first month it starts to unfold. And after about a month, it's unfolded and it's entering orbit around L2. And about 6 months later, it can start to begin its science observations. So after the JWST arrived at L2, months of testing and fine tuning went on to follow. And engineers worked to align the mirror segments to calibrate and be able to create these basically tests to make sure we were able to, everything was running optimally and we were able to get these really crisp, clear images from each of the onboard instruments. You can see here the alignment images where you see these lovely JWST PSFs, beautiful star fields from the different instruments that are on board. And the first images that were released in July of 2022 would confirm that it was working even better than expected and would really lay the groundwork. And we'll discuss the importance of that, but really set the stage effectively for what would be a lot of groundbreaking discoveries. Here, I'll skip past this, but this is just a full timeline sort of showing you from its arrival at L2 for the full telescope commissioning and science instrument commissioning. So I'll skip past it, but for those of you looking at the recording, you can pause and take a look and see the timeline in more detail. So as I said, these first images that were released, not all of these are some of the first images, but these are indeed beautiful images from JWST, showed that it was working even better than it was expected. And that's at that point that the public and scientists as well. I mean, I'm sure some of you perhaps were graduate students at the time, maybe, and were also just like completely blown away by some of the beautiful images, or undergrads that were coming out from JWST. And you know, whether you're a member of the public or a professional astronomer or anything in between, there's something very powerful about looking at these images. So now we'll shift into talking about science, JWST science in Canada and beyond. So JWST was designed to tackle a lot of fundamental questions about astronomy, and there are five main areas that it focuses on. These are effectively broad goals that have helped guide the telescope's mission and areas in which Canadian scientists are doing research. So some of the main questions include what did the early universe look like and when did the first stars and galaxies form, characterizing black holes and how they form and evolve, the life cycles of stars from their birth to their death, looking at planetary systems, including within our own solar system and how they form and evolve, and then certainly studying exoplanets and their atmospheres and in the context of the search for life in the universe. Now here I just have a quick grid, and this is what we call, so with JWST as an astronomer, there are different cycles for observations, and it's within these proposal periods where you can propose to do observations with JWST. And so the most recent cycle that has been released and confirmed, we just completed a proposal and application cycle. So cycle 4 just closed, and those proposals are currently under review. But these are the cycle 3 results. And you can see here, this is all a Canadian PI program. So you can see that the types of research that are being done span exoplanets. This is just in the past cycle. Exoplanets, looking at supermassive black holes, stellar physics, galaxy evolution, stellar populations, ISM work. And these are Canadian-led programs. And then you also can look at the Canadian co-PI programs. So these are jointly led by Canadians and or Canadian scientists. And you can see this also expands to large scale structure, more stellar physics, exoplanets, etc. And there's a link there at the bottom. You can look at some of the approved programs. If you're, depending on the type of science you do, you can start to see what maybe some science that's being done in your field with JWST. And get some inspiration for potentially applying for JWST time in the future. Although I think Ulrike will probably discuss the details of that in depth. I just wanted to pitch that and show that Canadian scientists I should say, scientists in Canada are definitely getting lots of telescope time. So of the science that's being done, as I mentioned, we had these 5 sort of main goals, and I'll just touch on some of the results that are there. So in terms of early universe and galaxy formation, JWST has been revealing just like record-breaking redshift galaxies, detailed spectroscopy, and helping us understand how galaxies evolved in the first few 100 million years. Canada secured guaranteed access to 450 hours of telescope time during the first few years of the JWST mission because of our contributions that we made to the telescope and the engineering. And this is through the GTO programs with the guaranteed time observations. And almost 200 of these hours are dedicated to the Canadian NIRISS Unbiased Cluster Survey. This is a CANX program led by Dr. Chris Willett from the National Research Council and HAA. And the CANX team is, in a sense, using gravitational lensing to study some of the earliest galaxies in unprecedented detail. One of their most significant findings, this was in 2022, was you might have heard about this was a sparkler galaxy. So after weeks of analysis, the CANX team concluded that they did observations. So this was one of the first images. I don't know if I can scroll back. You saw that was a deep field. They identified a lot of different objects, but one of them was a sparkler galaxy. And you can see there in the zoom in that you see on the right, the Hubble image. And then on the left, sorry, my dog is barking. You see these like orangey, reddish dots effectively. And these were, observed to be, at least 5 of them were observed to be globular clusters. But not only are they globs, but they are some of the oldest known globular clusters, forming only 500 million years after the Big Bang. So if you're less familiar with what a globular cluster is, these are dense spherical collections of ancient stars that orbit galaxies. They're typically found in the halos. And these clusters can contain hundreds of thousands of stars, and they're bound together by gravity. The Milky Way has over 100, and they're known to be some of the oldest stars in the universe. And so studying globular clusters helps astronomers understand how early galaxies evolved, and it helps us understand the chemical evolution of stars over time. And a big question that was outstanding about globular clusters is how old are they? Are they the oldest, for example, part of our galaxy? Are they some of the oldest stars in the universe? And the Sparkler galaxy and the paper that you see there, Mola et al. 2022, used data from JWST to start getting some insight into some of those questions. We found, they've identified that these were very, very old, and they formed very early after the Big Bang, which is a lot of support for globular clusters as being super, super old things that formed early on. In addition to that, more recently, we have a result from CANX in 2024. This was the Firefly Sparkle. So the CANX team identified a galaxy using JWST that is not only in the process of assembling and forming stars very early on, only about 600 million years after the Big Bang, but the galaxy itself also weighs in at about the same as our Milky Way galaxy. If we could wind back the Milky Way clock to weigh it as it developed. And so you can see here two companion galaxies also identified there close by. And so because of gravitational lensing, you can get really unprecedented insight into galaxy formation early on. And in particular, in the case of the Firefly Sparkle galaxy, which is an interesting name, you can start to better understand even like how our own Milky Way potentially, like what are the processes that might have led to the development of the Milky Way. And one thing I want to highlight about even Firefly Sparkle is that I was speaking with my colleague over at Space Telescope, and they were saying that these are the types of discoveries that really resonate with the public. In fact, Firefly Sparkle, I think she said, had over 10 million independent reads on some of the articles. So really popular, really viral type results. So yeah. Now, JWST Science in Canada is also addressing questions of planetary system formation. So here we have the PDRs for all teams. So at Western, you have Professor Els Peters, who is part of that team, looking at observations of the Orion Bar. So JWST has been able to provide us really detailed views of the Orion Bar, which is a photodissociation region that looks at how radiation affects planet-forming environments. And so Professor Peters' team, as part of the PDRs for all team, Professor Peters' group is studying complex hydrocarbons and dust grain evolution in these environments for trying to get a better understanding of how planets evolved. So you can see here this absolutely beautiful image from JWST of the inner Orion Nebula. And you can see an example of a young star inside a globule. You can see filaments and a young star with a disk inside its cocoon. I mean, just truly incredible images and really great science happening at Western. There's also work being done for brown dwarfs and rogue planets. So this is a collaboration with contributions from IREX. So this is the Traité Institute for Research on Exoplanets. This is indeed the institute in which I work for as outreach officer at Université de Montréal. So what you're seeing here, the main image on the right, that is a mosaic of a nearby star-forming cluster located within the Perseus molecular cloud. This is about 900 light years from Earth. And JWST's infrared capabilities allowed us to do detailed study of newly born free-floating brown dwarfs. And these are objects with masses that are about the same order as giant planets. Researchers at IREX contributed to a study of this region called NGC 1333 using JWST and to look at the star. It basically did investigation to the star forming region and found some of these free floating brown dwarfs have masses as low as 5 times that of Jupiter. And this type of work is really important because it helps us gain more insight into how stars and planets form in these smaller stellar nurseries. And it's really in some ways a benchmark for future observations into JWST observations looking into star and planet formation. Now, as I said, an important shift that's happening in exoplanet science is one from just sort of getting numbers about how many exoplanets are out there, but also looking into like characterizing the exoplanets themselves and building these holistic pictures. And I have 2 results here that are really good examples of that. The first one is, and as I learned, there's a lot of the exoplanets have these code names, right? So GJ 987 or 9827D. This is a paper led by a Canadian graduate student now, a postdoc at the University of Chicago, Caroline Pierre-Goriev. And she recently published a paper last year of the smallest known exoplanet with a confirmed atmosphere. This is a planet that is orbiting the star GJ 9827 in the constellation Pisces, about 98 light years from Earth. And it's about 2 times the size of Earth. And as I said, it's the smallest one to date with a confirmed atmosphere. So using transmission spectroscopy, her team analyzed the star's light as it passed through the planet's atmosphere during a transit, and was able to distinguish between 2 types of atmospheres for the planet. One that was cloudy with a few heavier elements, and one where and where water would only be present in trace amounts, to one that has a much higher density with heavier elements such as water being much more abundant, and was able to provide much more evidence suggesting that this planet itself is what's known as a steam world. So they were able to combine the JWST NIRISS data with HST data and find a significant presence of water vapor in the planet's atmosphere. And so this is quite interesting. And I've just put up this is another result that went quite viral. So these are some of the news clips that came out from Dr. Piolet's work. Another one that went viral as well was LHS 1140b. This is by Dr. Charles Cadieux, a graduate student at UDM, recently graduated. Congratulations to Dr. Cadieux. And this is known as the eyeball planet. So this is located about 48 light years away in the constellation Cetus. JWST time was collected in, I think, December of 2023. It was added to previous data from other telescopes to solidify this result that was published in July. And this was of this planet that is what has become known as the eyeball planet. So before NIRISS, before observations from JWST, we weren't sure if this was a mini Neptune or a super Earth, and it seems more like the latter. And this is an interesting exoplanet for which, tidal locking has created these surface features resembling a bit of like an ice ball with a liquid ocean, but because of the tidal locking, it actually looks more like an eyeball with a sort of melted-ish center, right? And it is emerging as one of the most promising habitable zone exoplanet candidates known because of the fact that it's expected to have this liquid ocean, sort of similar to Europa, for example. Yeah, and so this is another example of a result that became super, super popular in the news. From the perspective of a science communicator, I find these results incredibly interesting because it really is what allows us as scientists to connect with the public and provides a lot more visibility for the great work that's being done by scientists in Canada. And so I just wanted to briefly maybe I'll skip past this because I want to provide some time for questions. But one thing I just wanted to mention is that, there is this general impact. These beautiful images, these incredible groundbreaking results, some of the ones I've discussed, all coming from JWST, are incredibly important because it goes beyond, as you know, not all science is just pretty pictures, right? Some of it is really pretty figures, really pretty graphs. And some of it is, not all science is incredibly easy to translate for the general public. But the reason why I find it's so important that we connect the great science that's being done in Canada with JWST with the public is because things like these beautiful images and these incredible discoveries can have a truly inspiring effect on young people. I myself was inspired to become an astronomer because of images from the Hubble Space Telescope. And so as scientists, as you go out and potentially do science with JWST, I just want to remind you that your great work also can not only serve a purpose in terms of contributing to the greater body of knowledge as astrophysicists, but also can help in inspiring the next generation of scientists, right? So just wanted to make sure that I added that. so you all understand the impact of the great work that is being done. And so I think I'll stop there. Thank you for joining me today. If you have any questions, whether it be about JWST or about, as I said, doing outreach and education work or that career path, sort of alternative career path, feel free to just raise your hand and we can maybe use the next few minutes for questions. Okay, thank you.
Thank you very, very much, Heidi. That was such a great talk. Like, honestly, I really loved the beautiful infographics and the
We
marvelous
can thank
images.
ESA. We can thank ESA. ESA and NASA and CSA. It goes to show, you know, science communication work is often sitting there and thinking about how do you make good graphics that not only help communicate important information to the public, but can also help junior career people sort of get their foot in, you know, wade their toes in the water in terms of understanding how these instruments work and how telescopes come together. Yeah.
Yeah, no, this was really cool. I like you showed images from James Webb that I never even seen before.
Mm.
And like those are like wow, like it's such high resolution. Like I've been, you know, like for the years, since the launch of JWST, I've been getting a lot of like, you know, news and like I've been aware of at some level of what it has been doing, and
Mm-hmm.
some of the figures you showed, I've seen some of them, but it's so fascinating to me that I keep seeing new stuff coming out, and
Yeah.
like image after image, it's like wow, like I've never seen in my life before James Webb images that were as sharp as those, and it's
Yeah.
really fantastic. Like I think it's really kind of the golden age of like observational astronomy in that sense,
Yeah.
because like like I cannot imagine how better could we ever be, you know, like it's difficult to imagine how bit like you know how we can improve from that already amazing like
I
capabilities.
mean, we probably said that as well about HST, right?
Yeah,
The
yeah, no,
Hubble
fair.
Deep Field when it came out, that's the image that made me an astronomer. I remember looking at it as a kid and seeing it and thinking to myself, like, oh my gosh, I couldn't believe that we were
Mm,
able to look at what was a seemingly dark part of the night sky and every little bright dot, effectively, not all of them, but most of them were individual galaxies, kind of like our Milky Way. And that blew me away. And I couldn't imagine what came next. And now, as a science communicator, I'm privileged to be able to do that same kind of work. And I think the effect that it has on you is the effect it has on the public, is the effect it has on scientists. Like no matter, we're just humans, right? And humans, I think it is a very visceral experience to see these beautiful images and think about how much, not only how much do we have to learn, because one of the cool things about it is these are great discoveries, but they inevitably create more questions, right? So it's a bit of
yeah.
job security for astronomers, I guess, is we always can create more questions to investigate. But it also is just really powerful to have that kind of connection with things in deep space and be able to observe them, characterize them, investigate them. Yeah.
So,
Hey Heidi, great talk. I just wanted to poke your brain a bit. I'm curious with the JWST, there's been a lot of clickbaity articles that came out based on evolving research. I'm curious as a science communicator, what are
Yeah.
your thoughts on those types of articles? Do you think they're useful? They're in attracting public opinion, or do you think they're kind of um
Yeah.
dangerous, I guess, in a way, because it's misleading?
Yeah. So I mean, in terms of astronomical, like astronomy news being misleading, I think this is something that we have been struggling with for a long time. So, for example, there was recently in the news, you know, well, this has happened a few times, but the detection of potentially an asteroid on a collision course for Earth, et cetera, et cetera. And it often, it's, so in my role, I actually am this intermediary between the scientists and the media. And I realized how important it is to have a scientist in that role, because there is a very powerful tendency by the media to try and make everything clickbaity and extreme, and extremify our results, to the point of misinterpretation and inaccuracy. Like you said, I do find that there is a level of a little bit of dangerousness that comes from that. At the same time, the media has a connection to the public, right? And so as scientists, we need to work with our communications offices at the universities to leverage those relationships to be able to get the knowledge out there, because as we know, not everybody, in particular in Canada, the opportunities we have to learn about astronomy are very minimal in school, right? And so things like the media can play a huge role in sort of democratizing knowledge and bringing it to the public and allowing people to connect with cutting edge science. But you do have to be quite careful, and it is very tricky as a, as a science communicator. I've definitely been in the position of being interviewed for interesting things like, people saying that they've detected aliens or something like that, and news hosts becoming very aggressive and things like that. And it is not always comfortable, but it is an important job, and I think it is something that we need to be mindful of. Yeah.
Yeah, thank you so much for the detailed answer. Yeah. I guess quick follow-up. I'm curious how you feel like science outreach is doing in Canada in general. Do you think it could be improved? Are there areas that you see are kind of lacking? Or do you think it's in a good
Um,
place, I guess?
so I will say that I think science communication is doing quite well, and maybe I'm a little bit biased because I've been working in it for some time. What I think that we need to focus, what I think, so there's different ways you can see science communication. So there is the science communication that happens when you go on the news as a researcher or a science communicator and you translate the discoveries to the public, right? You're talking to news media, etc. And that's sort of like broad reach. But there's this other phase of science communication that happens that's much more experiential. And it's when you're working on running like outreach activities within communities. And in particular, one area in which I think we could stand to improve is making sure that we are targeting underserved and underrepresented groups, and especially at younger grade levels, to make sure that they are able to participate in science and build their self-identity as scientists. So that's something that I'm quite passionate about in my science communication and my outreach. And I think that's something that it's not lacking for lack of people science communicators not wanting to do it. It's just funding, right? So that is one thing that I would love to see improved on. Yeah. Do we have another hand up?
Yeah, hi. Hi Heidi,
Hi.
nice talk. I was just wondering how often like Canadian researchers that get like web time, how often they're like reaching out to you to do like press for like their results.
Not enough. I'll say this. So one thing that I have struggled with in this position is getting the word out to Canadian researchers who are doing work with JWST data, is to please contact me when you submit a paper to a journal. And we can start to have a conversation. That is my job, is to basically help Canadian scientists promote their discoveries in the media, and not just within Canadian media, but even beyond, right? And so if it's one thing that I could leave you all with, if you work on any sort of JWST data or you plan to, please remember that when it's time to submit a paper, or if you have submitted a paper, please fire me off an email. So that's heidi.white@umontreal.ca. And let me know about it, because although I might not lead the coordination of a PR, I can certainly help you understand the steps in promoting your research, getting it to, potentially doing a PR or a blog post or various other things. There's a lot of different ways in which your research can be promoted within Canada. And as graduate students, this is incredibly important because if you decide you want to pursue a career in academia or even not, raising your profile you're doing fantastic work, fantastic research, you're leading papers, and you deserve to have the recognition that comes with that, right? And it can help you in things like job searches, postdoc interviews, things like that, to be able to say, you know what, I published this paper and I did basically a press junket on it because I had like 10 different interviews in media, everyone interested in the work, and it really helps you in your career. So I would say to graduate students, please feel free to reach out. And I can help you understand sort of the process to promoting your research and who to give you emails of who to contact and advice on how to contact your press offices at your universities and institutions.
Thank you.
I have one last question, and then we will wrap up. About your career, like growing up from a grad student to now where you are as an outreach officer. Did like at any point in your graduate journey, did you ever considered becoming a professor, or were you always interested to become an outreach officer or working in outreach in kind of these things? Like, was it always your plan, or was there a shift at some point? And
there
why
was a shift.
did you shift? Yeah.
Yeah. So definitely as a graduate student, I started off my studies, even as an undergrad at U of T, I started off my studies thinking I want to be a professor one day. Like I was so sure that that's what I wanted to do. And I was at the University of Toronto. I was privileged enough to be working in a department that was near the Dunlap Institute for Astronomy and Astrophysics. They do a lot of outreach and educational events. And as a third or fourth year grad student, I had the opportunity to do a TA-ship. And that was the first time that I was able to teach in a sort of traditional setting. And I didn't think that I was going to enjoy teaching. Like I thought I was just going to be research, research, research. And then I decided I wanted to do a TA-ship. I wanted to make a little extra money. So I was a TA in my later years in undergrad. And I fell in love with it. It was not something I expected. I totally went into it thinking I was going to do just research. And it was such a rewarding experience. I realized that helping people understand things that they didn't think that they could understand is like, in some ways, one of the most rewarding experiences I can have. And so that sort of like I was like a gateway to doing even more outreach and education, right? I did more TA-ships. I went into grad school, and there were, as I said, because I did my PhD with Dunlap, there were so many opportunities for me to do outreach and education. I realized in hindsight that I think a lot of it was that there was a lot of support from my department, and not every grad student gets that same level of support in terms of pursuing things outside research. I'll stop there, but if you have any questions about that and like how to be able to run these things in parallel, I'm often asked about that. You can feel free to email me and we can discuss that offline. But I really had a lot of support. And so it allowed me to do things like in my second year of grad school, first year of grad school, co-found a school in Africa. And that school has been running for a decade now. And have the experience of going there and teaching in different communities with different populations and people who don't necessarily learn in the same environments in which I grew up learning, and have all of these experiences. And all of that together really is, I love research. I love galaxy research, and I enjoyed my PhD immensely and research I did in it. But eventually, over time, there was a shift that happened in me, and I found that my true calling was to work in science communication and education. Yeah. So
Very inspiring. Thank you so much. Okay, I think it's time to finish the talk. I'm gonna turn off the recording.